Hello, my name is Sangook from Mokwan University, Korea. Today, I'm going to talk about a topic, self-reconfiguring pseudo-random address generator for secure infrared communication. Please let me begin. Infrared communication has its distinctive weaknesses and strengths. Open-sight between transceivers should be guaranteed. Transmission scope is relatively short, and obstacles are not allowed. Despite all, on the other hand, with conditions met, the communication benefits extremely low power, and the cost of the infrared sensors are economical. Therefore, in a specific environment, infrared communication can become a perfect solution for short-range, low-power applications. Wireless sensor-based hazard detection system in a nuclear power plant is one of the applications that need the least power as possible, gathering continuous data from thousands of sensors. This unique electrical communication environment requires restrictions of electromagnetic interference and radio frequency interference restriction for safety, which places the infrared communication in an outstanding position in a special purpose environment such as a nuclear power plant hazard detection. Cyber attacks, however, on energy facilities around the world, including nuclear power plants, have been emerging over the last decades. The Stuxnet case in Iran, wind turbine system shutdown attack, the Ukrainian power grid attack, etc., show that virtual threats can harm the safety systems, causing immediate halt of the facilities, malfunctioning the control systems, and the physical damage of the electronic and mechanic equipment. In this contribution, we regard our target application as a nuclear power plant communication system. Out of many security issues, we discuss the security of the infrared communication between thousands of sensors, keeping our focus on the minimum power consumption. We propose a low power consuming pseudo-random number generator featured by self-reconfigurability. One of the standard protocol for infrared data transaction is the NEC protocol. The protocol uses pulse distance encoding, where each bit comprises a pulse and a space. Each pulse is carried at the rate of 38.222 kHz frequency, resulting in the length of 56 2.5 microsecond duration. Logical false is denoted by a 562.5 microseconds. And a 562.5 microseconds space back-to-back, resulting in a total transmission time of 1.125 milliseconds. On the other hand, logical true is denoted by a 562.5 microseconds pulse burst and a 16,875 microseconds similarly, resulting in the total transmission time of 2.25 milliseconds, shown in the figure. We target our application focus on the communication between sensors within a nuclear power plant. So we modify the standard NEC protocol to meet the system requirements. Since the number of sensors are required in the scale of thousands, we suggest the number of the address bits as 16. Otherwise, we stick to the standard protocol, where 8-bit data bits are enough for hazard detection. Total transmission time for 1 byte is approximately 176 milliseconds. Rindle S boxes are cryptographically reliable permutation tables used in advanced encryption standard data encryption standard with 8-bit input and output. Due to its nonlinear substitutive characteristics, we can utilize its statistic peculiarity to generate 8-bit pseudo-random numbers. No matter how cryptographically strong a fixed structure of substitution box may be, however, it should become vulnerable over time. We propose a 16-bit simple but tricky permutation pseudo-random number generator architecture with self-reconfiguring feature shown in the figure. First, we divide the address into two parts. We apply each 8-bit part through the S-box tables to have randomness characteristics to create a 16-bit random address. In view of infrared communication, transmitting sensors equipped with CPU systems and the data gathering node have the same forward-inverse S boxes. With the suggested IR protocol, 1 byte data will be transmitted according to the address identification, and both nodes know when the transaction ends. At this time, the higher 8-bit of permutated address is XORed with the higher 8-bit unpermutated address, acting as a random seed value to the permutation box. Similarly, we perform the same sequence to the lower 8-bit address. In this way, every time a byte data is transmitted, the address of transmitting sensor data will be self-configured as a random number, and the receiver node can verify the transmitter node address in the same way without fail. Transmission time for 1 byte data is 176 milliseconds, and this period is long enough for the embedded transceiver computers to reconfigure the new random address. Next, evaluation. In the figure, the result of outputs of the proposed self-reconfiguring random address generator with experimental inputs of 2000 incremental transmitter address is shown. Statistics show that the mean value of the output address is 31,000 963, and the standard deviation is 18,944, which are proper characteristics for random numbers generated between 0 and 65,535, which is 16-bit possibilities, all of them. Also, each generated address has its unique value, which does not collide with any other addresses. This proposal of pseudo-random address generator is a part of an ongoing project in which more than 100 transmitter sensors are matched with one receiver sensor using infrared communication system in a nuclear power plant. So, more than randomness and uniquenesses are required to properly evaluate the proposed design of the address generator. More issues to be considered will be discussed in the expanded work in the near future. Finally, the conclusion. We propose a self-reconfiguring pseudo-random address generator for thousands of sensors in a secure infrared communication transaction, which is applicable to a hazard detection system for a nuclear power plant. Proposed address generation architecture eventually hides the address of a sensor with simple but tricky mechanism, showing cryptographically reliable characteristics. Also, it only has two 256 entry S-box tables and need trivial XOR operations so that infrared communication will still take advantage of ultra-low power attribute without any overhead. This contribution is a part of an ongoing project, so we are implementing this architecture to build the secure infrared communication between thousands of sensors. We strongly believe that this work will contribute to prevent security issues from cyber attacks in many sensor-based hazard detection systems. Thank you for listening.